Let me give some number like that. All will be of same size. I'm unable to draw them. Twenty-two. Okay, we'll look at this 35. Then we'll. These are the numbers. I think I numbered everything. You look at the one. So what is the nuclear force? Nuclear force is a short range force, no? So altogether, how many? I think what is the maximum? So we took around 65 nuclei. So total number of nuclei, how many are there? Total number of nuclei are 65. Is it each and every nuclei will interact with every other nuclei? The answer is no. So now if you look at the nucleus one, what happened? Will interact with 28, 27, 17, 2, 3, 18, 29. Will interact with these surroundings. Will interact with these surroundings. So I'll just only take one, I'll explain. I think the middle one, let me write one. Now let's take the one. One is our center point of this one. Let it interact. Let's see that with what all it's interacting. Let me focus only on one. Now, if you look at the one is it interact with all the nucleons, all the nucleons? The answer is no. Total number of nucleons. Sorry, this is total number of nucleons is 65. That one. So one is interacting with what? Say 2, 7, 15, or you can say within this boundary. So somewhere till here, what happened? It is able to interact. One cannot interact with say like a 40, 43 or 65 or 61. Any reason for that? Nuclear force is a short range force. So this will be say like by the time this will be 1 femtometer. And how much this distance will become between 1 and 28? Maybe greater than 1 femtometer. Then what is the distance between 1 and the 53 year? So that will become more than 1.5 or around 2 femtometer. And what is the distance between 1 and 61 will become around 2.5. And according to the graph, if the distance becomes more than 2.5, already there is interaction. Just around 2.5, the distance between the nucleons become more than 2 or 2.5, there won't be interaction. So shall I say that the interaction gets because of saturation, because the nuclear force gets saturated. Yesterday I drawn one curve. You have to recollect that. So therefore, the interaction depends also on the distance between nucleons. So one will not interact with all the nucleons. So let me focus only on one. So what are the points? I'll put it one by one. Nucleon 1 will interact strongly with say What are the surroundings? 3, 5, 15, 2, 3, 5, 2, 3, 5, 15, 17, 18. Let me come in order. 2, 3, 5, 15, 17, 19. 4 is also there, no? Yeah. Will interact with this strongly, that one. Next, if you go for outside, so I'll give different colors. That interaction, I'll give different colors. So if there's a strong interaction, rough to make you understand. So what happened to the one? One will interact with 6. What happened to interaction? Will decreases. So as you move away, the interaction it decreases here. So this you look at this, the green color. So the interaction decreases. With respect to one, we'll discuss the problem so that we'll understand this one. So what happened now? So nucleon one will interact strongly. So what happened to next year? Nucleon interact moderately, I'll say moderately with green color nucleons. Green colored, rather than numbering, no, I'll write like this: green colored nucleons. This is what nucleon 1 will have very weak, I'm using word very weak or no interaction. No interaction with what colors here? Because they're far away, and the nuclear force is what? Short range force, no? No interaction with brown colored nucleons. So like this, what happened? The whether the nucleus is stable or not will determine how many nucleons. Means most of the nucleons, if they have strong interaction with nearby nucleons, then the nucleus is said to be stable. Later on, the stability, I'm going to take help of the same condition. So this is what happens here. Now the same thing. Now it's not only one. Sir, I'll take 12. Now you look at the 12, this particular thing. If you look at this one, this particular 12, the 12 will interact very strongly with this. Next it will almost interact with this, and the 12 open will weakly interact with 39. Also like these particular things. The 12 open will weakly interact here. Or if you look at the adjacent, the 43 and 39, they will, shall I say, weakly interact. The 43, what happened? Will weakly interact, almost there's no interaction. So like this, as the nuclear force is a short range force, so the interaction between the nucleons depends also on the distance. So almost you can say it gets saturated. No interaction between 39 and 43. So all the nucleons at open are not strongly bound. So these outermost nucleons, shall I say that they are weakly bound. So inside the nucleus, what I noticed that the outermost nucleons are weakly bonded. Weakly bonded. And moreover, you come for, if you look at the 3943, if you see 1915, so let me take the 1 and the nucleon 15. So there'll be an interaction force. The nuclear force I should not show, but to make you understand, I'll show like this, not straight line, something. So there's a nuclear force. So let both be proton, 1915. Let both be proton. There'll be electrostatic force also will be acting. But here what will happen? Fn will be very much greater than electrostatic force. as they're very tightly bound, 1 and 15. But if you look at the 43 and 39, if you look at the 43 and 39, 33, what is 39 and 43? If you look at the 39 and 43, so what is the nuclear force? Is almost zero. And let there be proton. Let there be proton. In that case, what will happen? The electrostatic force, again, it's a long range force. At a distance of order few femtometer, the electrostatic force will not be dominant. Once the distance becomes 3 or 4, 5 femtometer, no, the electrostatic force will be dominant. Fe will be dominant. Here what happen? Fe is weak because the long range force at a distance less than femtometer, it will be 2 or 1 femtometer. No, the electrostatic force will be weak, and the nuclear force will be dominant here. No, this what practically happened. So like this, what happened? So many conditions will come, and the binding energy depends also on this. Is what I wanted to tell you that one. So when the distance between nucleons becomes greater than 3 femtometer, almost the nuclear force will become zero. No, I think a graph I explained everything there. That graph is what actually you're supposed to keep in mind. You have to measure the distance between nucleons, whether they'll interact or not. And sometimes it'll be repulsive. Repulsive between what? Between nucleons if they come very close. Of course, we'll not bother with the repulsive force here. Only attractive force is what we'll discuss about this one. I'll not show Fn, second case, because it's not at all existing, got saturated. So and the